Hello everyone. Welcome to the sixth lecture on the lecture series on open channel flow. This is the continuation of our discussion on the energy depth relationships for open channel flow. Um, in the last couple of lectures, we have discussed extensively the basic aspects of the energy depth relationships, and we have calculated the critical depth for open channels of different cross sections. Now, in this lecture, we are going to apply the knowledge of the energy depth relationships to analyze another important aspect of open channel flow, which is the transitions in open channel flow. We'll start with one example of the transition. There can be many types of transition. Now, in this lecture, we are going to discuss only a couple of them. Uh, we'll start with the hump in an open channel flow. So hump is the essentially change of the channel of the height of the channel bottom. So you can see in the diagram on your right that there is a hump in course of the open channel. Uh, the depth, the channel bottom height changes from a lower height to a higher one, and that is called a hump. Now, we are going to consider a rectangular channel for our analysis. The same analysis can be applied for channels of other cross sections as well, but for simplicity, we are going to consider a rectangular channel. And the rectangular we will further consider the rectangular channel is carrying a subcritical flow, and the rectangular channel is frictionless, so there is no frictional head loss in the channel. The width of the channel, let's assume to be capital B, and the discharge through the channel is capital Q. So as you can notice that as there is no frictional head loss in the channel, so the total energy line, as shown in the figure on your right, that the total energy line is a constant one. So the elevation of the total energy line is not going to change. We will also consider two sections for the analysis, section 1 and section 2. Section 1 is in the upstream of the hump, and section 2 is right on the hump. Let's also assume that the height of the hump here is delta Z. So note one very important thing here, that although the total energy is not going to change as there is no frictional head loss in the channel, but the specific energy, the quantity of specific energy is going to change due to the existence of the hump in the channel. This is because we know that total specific energy is a quantity which depends on the relative position of the total energy line with respect to the channel bottom. From the definition of specific energy, you can remember that specific energy is something we define as taking the channel bottom as the datum. Now, if the channel height of the channel bottom changes, then the datum is going to change as well, and thus the critical energy, the specific energy is going to be affected. So since we assume that the height of the hump is given by delta Z, so the specific energy in this case is going to be reduced by an amount delta Z when the flow happens over the hump. So as we mentioned in the last slide, that we can write the specific energy of flow upstream of the hump as E1 at section 1 as E1 is equal to Y1 plus capital V1 square by 2G, and where Y1 is the depth of flow upstream of the hump, and V1 is the cross-section average mean velocity of flow upstream of the hump at section 2. Whereas the specific energy at section 2, E2, capital E2, is equals to E1 minus delta Z, as we already mentioned. Now, let's focus on the critical energy diagram at the bottom. So the critical energy, this is the critical energy diagram for a constant Q or constant discharge, and if we as this flow is a subcritical one, we have to focus on the upper limb of the diagram, and so the point P, which corresponds to the specific energy E1 at section 1, and depth of flow is Y1. You can see that as we reduce the specific energy of flow by an amount delta Z, the point P shifts to a new point R with a lesser depth. As you can see that that is given by the point R, and the specific energy is reduced to a value E2, which corresponds to point R. So here in this case, as you can see that due to the existence of the hump, the flow depth reduces to a value. So essentially, hump is something which existence of which reduces the flow depth. It can be also seen from the specific energy diagram that as we further increase the height of the hump, the specific energy reduces further, and the height of flow is going to be further reduced. So that you increase the height of the hump, the downstream flow depth at section 2 is going to be reduced further. So, and this reduction of flow depth continues with the increase of hump height as long as it doesn't reach the critical condition. Please note at the in the specific energy diagram that point C gives the critical condition, and for a specific discharge, so the specific energy can be reduced only to a value up to the critical energy. So beyond the critical energy, or if we further increase the height, so any flow is not possible because there is no positive root which exists for a specific energy less than the critical flow energy. So we call this the maximum height of the hump at which the flow conditions reaches the critical condition as delta Zm, as also shown in the specific energy diagram, and the condition of flow over the hump then reaches the critical condition, and the corresponding specific energy is the critical flow energy, which is given by the last equation of the slide, given by E2 is which equals to EC, or the critical energy, critical flow energy, which equals to YC, that's the critical flow depth, plus capital QC square by 2G capital B square into YC square. So now try to imagine a condition uh, for for which delta z is greater than delta zm. So uh, so when the hump height is greater than delta zm, there is of course no flow possible with the given upstream flow conditions, as the as the specific energy downstream becomes less than the critical energy. So this particular condition is called the choking condition. The choking is a condition when the upstream flow with a given specific energy chokes or is unable to pass due to existence of a high hump. So such a condition, as you can of course imagine, is very much undesirable, and while designing open channels with transitions like culverts and other drainage channels, it should be kept in mind that the height of the hump should be such that there should be no choking uh, uh, for the given flow conditions. Now, here in all our discussion so far, we didn't consider the upstream height flow depth y1 to be affected. So y1 remains unaffected for the whatever we have discussed so far, and only we have considered the change in the downstream flow depth y2. So, as we discussed that when delta z is greater than delta zm, no flow is possible. The flow attains the choking condition, and so flow is not possible. Remember, flow is not possible with the given upstream flow conditions. Now, to continue the flow, something has to change, and that has to be the flow depth. For the same discharge, of course, for the same discharge capital Q, if the flow has to happen, then the upstream flow depth y1 has to increase. So if the upstream flow depth y1 increases, the specific energy of flow increases, so that the flow again can continue. Now, to what extent should the upstream flow depth increase so that the flow can again happen? So we can imagine from the diagram again that upstream flow depth y1 has to increase to such an extent that the downstream flow condition at section 2 should at least reach the critical condition. So at the new upstream flow depth, which is called y1 prime here, the specific energy can be given as the equation E1 prime equal to y1 prime plus capital Q square by 2g capital B square y1 prime square. Note that here E1 prime is greater than E1 and y1 prime is greater than y1. The downstream specific energy is of course the critical energy, as we discussed. So E2 is equal to EC is equal to YC plus capital Q square by 2G capital B square YC square. Now, so far we have discussed about subcritical flows. Now, what if the upstream flow is in the supercritical flow regime? The supercritical flow, as you can see in the specific energy diagram at the bottom, that the specific, of course, the supercritical flow is represented by the lower limb of the specific energy diagram. And if such a flow encounters a hump of height delta z due to the reduction of specific energy the point P shifts to point R, and the point R is a point with a larger flow depth. So here, unlike the subcritical flow, due to the existence of the hump, the supercritical flow attains a larger flow depth. Uh, so the larger flow depth is termed as Y2 here, and so E1 is greater than E2, and of course Y1 is less than Y2 here in this case. So you can see here that as we keep on increasing the height of the hump, the specific energy reduces further, and the supercritical flow depth Y2 keeps on increasing, and it keeps on increasing till the critical flow condition is reached. The height of the hump corresponding to the critical flow condition is the maximum height delta Zm, which can maintain the flow with the given upstream conditions, and the specific energy for the maximum possible hump height here, or delta Zm here, is E2, capital E2, which equals to EC, which equals to YC plus Q square by 2G B square YC square. So of course, if we increase the hump height further, as the specific energy reduces further and goes below the specific the critical energy, then of course the flow with the given upstream conditions is not possible. So the flow again chokes. So this is again a choking condition that the flow attains. So again, if the hump height is bigger than delta Zm, so to maintain the flow or to continue the flow with the given discharge capital Q, we have to increase the upstream flow condition. That is, we have to increase the we have to decrease the flow depth here. This is the supercritical flow, so we have to decrease the flow depth. So decreasing the flow depth in the supercritical regime of flow means that you are increasing the specific energy, and the new increased specific energy is E1 prime. With this new specific energy, the flow will continue, and the downstream flow condition will be at least the critical condition. So the downstream specific energy, which is given by E2 prime, which will be equal to YC plus Q square capital Q square by 2G B square capital B square into YC square, as shown by the last equation of the slide. Now from the example of the transition given by the hump, we will now move on to the discussion on another example of the transition given by the width constriction in the channel. So in analyzing the flow, our assumptions will be the same here. That is, the channel we consider will be a rectangular one. The width of the channel is B1 at section 1, capital B1 at section 1, and capital B2 at section 2. The channel is of course carrying a discharge of capital Q. The channel is frictionless, and one more assumption is that the width of the channel is gradually and smoothly constricted to attain the downstream width constriction. So the width is reduced from capital B1 to capital B2 smoothly, and gradually, so that there is no head loss due to this due to sudden constriction in the channel. Now you can imagine here that as there is no uh, there is no change of the datum for the flow, there is no increase of the height of the channel bottom, increase or decrease, whatever. There is only change of width of the channel. So the specific energy of the flow is not going to change here. The specific energy will be the same, that is capital E1 at section 1 will be equal to capital E2, which is given by the last equation of the slide. Now, although you see that the total discharge through the channel remains constant, due to the change of the channel width of the channel, the discharge per unit width or the discharge intensity given by small q, which equals to capital Q by capital B, becomes a variable here. So as you can see, capital B1 is greater than B2, so small q1 will be less than small q2. So the specific energy diagram can of course be drawn for different discharges or for different discharge intensities. In the specific energy diagram on at the bottom, you can see that different curves, different cubic parabolic curves have been drawn with the specific specific discharge or discharge intensity as a parameter. So in this diagram, in the specific energy diagram, as we increase the discharge intensity, the curves shift rightward, and that's for a specific for a given specific energy, uh, the flow depth flow depth actually changes to a lesser one. So here for the point P, which corresponds to the specific energy E1, the upstream specific energy, shifts to another point capital R, which is on another curve for another discharge intensity Q2, and you can see that the height, the flow depth corresponding to point R is lesser than the flow depth corresponding to point P. So here the meaning of all this, the gist of all the discussion is that due to the constriction of the width for a subcritical flow, the flow depth reduces in the constricted section. So of course, if we go on reducing the width of the channel, the specific the discharge intensity increases further. So the curves shift rightward, and as a result, the flow depth decreases further. So this actually this process goes on till the specific energy till we reach the critical flow conditions. So the maximum discharge intensity possible at the critical condition is small qm, and the corresponding uh, maximum reduction of the width of the channel can be reduced to a maximum of capital Bm. Uh, so beyond this critical condition, of course, maintaining the upstream flow, maintaining the flow of given discharge capital Q with the given upstream conditions will not be possible, and the flow will attain the choking conditions again, which will be avoided, of course, in the real life flow problems. And to Here in this slide we are calculating the maximum possible reduction of the channel width, or the minimum width of the channel to which it can be constricted so that the choking condition doesn't happen. So this specific energy at the critical flow is given uh, by the first equation of the slide. Capital E2 is equal to YCM. That's the critical flow for flow depth, critical flow depth for the minimum width cross section, plus capital Q square by 2G capital B2M square into YCM square. And also note that here, as we mentioned before, that the specific energy does not change here, so E1 will be equal to E2 here. We also have derived for the critical flow conditions in a rectangular channel, YC is equal to 2/3 of EC. That's the critical flow depth is 2/3 of the specific energy at critical condition. So since E2 is equal to E1, here we can write Y2 is equal to 2/3 E1. So that's we can write for the critical condition. Also, we know we derived another result for the rectangular channel, that the critical depth given by YC equals to QM square by G raised to the power 1/3. So these results are used to calculate the minimum constricted width downstream, which is given by capital B2M, and which can be easily derived as under bracket capital Q square by G YCM cube to the power half, or B2M equal to under bracket 27 Q square by 8G E1 cube to the power half. So this is essentially the minimum width of the constricted section for which flow can be maintained with the given upstream conditions. So if we further increase reduce the width of the cross section with the given upstream conditions, there is no flow possible, as we mentioned repeatedly. So to maintain the flow, to continue the flow, the upstream flow condition has to change now. So the upstream flow depth has to increase to a new value given by Y1 prime, so that the specific energy attains a higher value given by E1 prime, which equals to Y1 prime plus Q squared by 2G capital B1 squared into Y1 prime squared. So the flow of course the at this condition the downstream flow condition will be a critical one, and the critical flow depth will be given as YC2 is equal to Q2 square, small q2 square by G to the power 1/3. Now note one important thing here, that capital B2 is less than capital B2M, so small q2 will be greater than small q2m. So the flow depth, the critical flow depth at this increased specific energy condition, critical flow depth downstream YC2 will be greater than YCM. So this result is indeed contrary to the previous case of the hump in the channel, where the depth of flow on the hump was constant. Remember, we increased the height of the hump, but the flow depth, the critical flow depth on the hump was constant with the changing upstream depth. So of course, when the upstream flow is in a supercritical flow regime with the given conditions, as as the discharge intensity increases, the flow depth increases as well, because this is a supercritical flow. And for this supercritical flow, represented by the lower limb of the specific energy diagram, we can see that for the point P prime, which corresponds to the specific energy E1, due to change in the discharge intensity, the point shifts upward to a new point R1 on a different curve, uh, which corresponds to the discharge intensity Q small q2. Uh, so the flow depth here increases, as we can see by the schematic at the top. So and this increase of discharge, the increase of the flow depth will happen till again the critical condition is reached. So reduction of the width further will choke the flow, unless the upstream flow depth changes. So the upstream flow depth here has to change to a smaller value corresponding to a higher specific energy to maintain the flow. So that's pretty much what we had to cover on the energy depth relationships for open channel flows. In the next upcoming lectures, we'll start the analysis of the uniform flow in open channels. Thank you very much.